Добрый вечер, Юрий. Good evening, Yuri, dear participants. I'm director of the Russian Center for Culture and Science in Paris. I'm very happy to welcome you all to the first purely scientific online conference at our center. And now let me introduce our guest. Mr. Kovalev is Doctor of Physics and Mathematics, Professor of the Russian Academy of Sciences, member correspondent of the Russian Academy of Sciences. He is also head of the Extragalactic Radioastronomy Laboratory in the Astrospace Center of the Lebedev Physical Institute of the Laboratory for Fundamental and Applied Research and Relativistic Objects of the Moscow Institute for Physics and Technology. Mr. Kovalev had two postdoc positions in National Radioastronomy Observatory in the USA and Max Planck Institute for Radioastronomy in Germany. Mr. Kovalev is a specialist in the field of the physics and active galaxies, interstellar medium, and radioastronomy. During his scientific activity, he conducted observations at most of the largest radio telescopes and radio interferometers in the world, and also used the Spectre R-Space telescopes of Russia, Halka of Japan, Fermi Swift of USA, etc. Our moderator today is Marina Ignatieva, head of the science section in our center. She will help to refer your questions to the speaker. I would like to wish all of you a fruitful conversation. Now I will give the floor to Marina.
Hello, everybody. We are very pleased to see you, well, to welcome you in our center, even though virtually today. I would like to ask all of you if you hear us well and if you see everything, please respond in the chat. So I'll wait for some answers to make sure that you hear us. Okay. Okay, thank you very much. Thank you very much to everybody. So I would like actually to tell you that as soon as you have questions for Mr. Kovalev, please just raise the hand. You can do it virtually in the Zoom, and I will give you the floor to ask your question. And then Mr. Kovalev, please, the floor is yours.
Okay, thank you very much. Hello, everyone. Guys, please give me some seconds, some organizational seconds. I will right now share with you my presentation and also stop my video to make sure that I use the internet from my home in Moscow in the most efficient way. And also, I was sitting right now. I am standing because there is no way I can give a lecture sitting while sitting, so I will stand. Okay, I would like to ask Marina to confirm that right now you still can hear me well, and now you see the first slide of my presentation the way how it is meant to be.
Yeah, that's right. Everything's right.
All right, everything is fine. Very good. Okay, let me start. Okay, guys. So I will present to you today scientific and actually technical results from a very unusual space mission, which was developed, built, launched, and operated by us during the last several dozen of years. Let me begin. And since I know that most probably people who are right now participating in this lecture might have different background in astronomy. Let me start with an extremely quick crash course on what we call interferometry, to make sure that we all are on the same page here. And before I start, let me also make another comment that while I'm giving the lecture, I was asked to prepare not a public talk, but a professional scientific talk. So I will discuss specific details on a scientific level of technological and scientific results which we have achieved. However, I will try to speak in on not very deep level, so that many people, even not having background in what I am discussing, what I'm presenting to you, might understand, appreciate, and enjoy what I present to you. However, on the slides, there will be more details. So if you want to see more details, you can take a look at what's written on the slides. You can read the references which you will see on the slides. And if you don't understand something, but you are interested in, or you want to hear details, don't hesitate to ask me questions during the lecture or after the lecture. Okay, let me begin. When I'm taking some gaps in time, this means that I'm drinking water. All right, crash course in interferometry is right now on your slide. For every telescope, it is extremely important. Every telescope has several key parameters which determine its capabilities. And one of these parameters is angular resolution. Angular resolution defines how large or how small are details of a structure of space object which we can resolve and study with a given telescope. From the course of physics which everyone gets in high school, hopefully everyone gets in high school, you should know that an angular resolution of a single telescope, of a single dish or a single lens is roughly calculated as the wavelength of your observation divided by a diameter of your telescope. If you are a radio astronomer, as I am, you are in a very bad position, because while we can build indeed the largest telescopes in the world on the size of, let's say, 100 meters, there is one close to Paris. Sorry, not in France, in Germany, but still close to Paris. When I was living in Bonn, so in Elfsberg, there is 100-meter telescope. It was indeed close to France. We were enjoying a lot of wonderful French cheese. Thank you very much, guys. We can even build larger telescopes, like 300-meter, which is located in the United States, in Puerto Rico, or even 500 telescope, which is right now in China, unmovable though. So you see that we can, by calculating this angular resolution, diameter might be quite large. However, the wavelength is even larger in a sense that you can show by your hands the size of the wavelength which you observe at, right? So it might be 1 meter, 10 centimeters, 1 centimeter, something like that. So when you divide one by another, it turns out that your angular resolution is extremely poor. Whatever object you observe on the sky, you will see just a dot. And so I'm trying to show it on the right-hand side of the slide. Every or almost every single dish radio telescope, whatever object you observe on the sky looks like a dot to you. Okay, what should we do? In the middle of the last century, about 50 years ago, our colleagues have suggested an idea of a so-called radio interferometer. Moreover, I'm discussing right now a so-called very long baseline interferometer. The idea was actually suggested by Soviet scientists, Matveyenko, Kardashov, and Sholomitsky. As it quite often happens, idea was suggested by Soviet scientists and first realized by our American colleagues. And here I use as an example, on the left-hand side, two 100-meter telescopes. I don't know if you can see my mouse, probably not, my pointer, I mean. So 100-meter telescope from Bonn, Effelsberg, and another one from Green Bank in West Virginia, United States. So we have learned how to join telescopes in a single system, which we call an interferometer. We record the data at both telescopes, and we have to synchronize these observations to very high precision. We will discuss it later in more details. And after doing that, we correlate the data, so perform special data processing. And after reducing the data, we can reconstruct images of space objects already to an angular resolution, which is calculated by the following question, right? So we have again the wavelength of our observation divided now not by the diameter of a telescope, but by the baseline. So that is why letter B, by the distance between the telescopes. And surprise, surprise, from being the poorest, we got the highest angle resolution in astronomy. So just because we can unite telescopes which are located all around the globe. And so our dot, which we were seeing previously, right now becomes a smile. So we see that someone is smiling at us from the space. Okay, how can we improve the angular resolution even further? Apparently, as you can see it on the slide, we can launch one of the telescopes into space. And that is exactly what we have done. As a result of that, in case of Radioastron, we have improved the angular resolution by an order of magnitude, and now we can see very well, can recognize the face which is smiling at us from the sky. And why is it smiling at us? Yes, it is smiling at us because 100 years later, but we managed to prove that Einstein was right and gravitational waves exist, and we were able to detect them. All right. So the crash course on radio interferometry has finished. Now you all know what it is. And this is just one of examples of a so-called global very long baseline interferometer. And it consists just of a number of largest and most sensitive radio telescopes around the world. Altogether, there are probably more than 100 radio telescopes around the world which are capable of being members of participating in this kind of observations. And so here's an example what you can do with that. So in the top left corner, you see an image of a hot plasma which is ejected away from the center of a quite nearby galaxy, M87. You all must have heard about this galaxy because of the black hole shadow result, which was announced almost exactly 1 year ago. And this is the ejection of a hot plasma. So Hubble Space Telescope on the top left. The rest of the picture, you see an image of the same jet, of the same ejection, which is produced by a ground-based global VLBI, very long baseline interferometer. And the resolution, the level of detailization of this image is 100 times higher than what you can see on the Hubble Space Telescope photo of the same jet. Basically, all what you see on the screen and many screens to the right from you, all is located within this bright spot in the left part of that image from the Hubble Space Telescope. If you don't know that, we radio astronomers and very long baseline interferometers can be also useful to study the Earth itself, and can actually be useful also for many applied tasks. So here there is an example of us measuring the velocities of different places on the Earth. How is it done? So you now know, right, that we can reconstruct images of extremely distant objects, right, of other galaxies. But we can do an opposite. We can perform an opposite task. So we can use these extremely distant quasars, extremely distant objects as reference points and measure positions on the Earth with extremely high precision, better than 1 centimeter, thanks to that, using these very long baseline interferometers. And this picture shows actually a collection of data coming from these interferometers and some other technique. Anyway, you can see here that we can measure the speed of plates which move on our planet, right? For example, again, actually, I don't know. So Marina, this is important. We didn't check it with you in advance. I'm sorry. Can you tell me if in webinar people can actually see my pointer? Can I use it to show things on the screen, or can I not do it, Marina?
Yes, we can. We can.
Oh, you see my pointer. That is wonderful. All right. So now, Marina, tell me, at which part of the Earth am I pointing right now?
The part is now it's Africa.
Yeah, you're right. Very good. Yes. Thank you. You see, I don't trust anyone because I am an experimental scientist. We don't trust even ourselves. Thank you, Marina. All right, so here is Africa, yes, and you can see that a vector of this length shows to you a direction of the motion with a speed 5 centimeters per year. So for example, if you look at this part, which is Europe, you see that Europe is moving altogether with a speed even more than 5 centimeters per second in the direction of Moscow. Unfortunately, Moscow is moving with the same speed away from Europe, apparently because it's the same plate. Okay, let's go further. We are also using very long baseline interferometry in order to measure Earth rotation parameters. And this is absolutely crucial to support the global navigation systems like GPS or GLONASS or you know, Chinese or European systems being right now built. Almost every day, at least twice a week, experiments are done observing distant quasars by radio interferometers in order to measure the direction of the pole axis, so pole coordinates. And here on this slide, you can see how pole coordinates change in time. This particular example shows to you the motion starting from the early 2010 through 2011. And you see that the pole moves with the amplitude about several hundred milliarc seconds on the sky. And a very accurate measurements are extremely important for in order for these global navigation systems to actually deliver the required accuracy of their of position determination. Okay, enough about the ground-based results and applications. Let's go to space. So here is an example of not an example, it is a cartoon of how to better say it, a virtual telescope, virtual radio telescope of the size of a distance from the Earth to the Moon. Because we have launched our 10-meter in diameter radio telescope with the name Radioastron into space, and our orbit has the apogee about 350,000 kilometers. It is more than 10 times larger than the diameter of the Earth. It is almost the distance to the Moon. And thanks to that, we have improved the angular resolution available to astronomers from the ground-based telescopes, ground-based interferometers by more than an order of magnitude. And here you can see photos of our telescope. On the left-hand side, you can see it's being furled. So it is 10 meters in diameter. It consisted of 27 petals. It was launched from the Baikonur launch pad in 2011 by the Russian-Ukrainian rocket Zenit 2. And several days later, it was unfurled. And you can see here, it's in Lavachkin Association being tested. So Lavachkin Association in Moscow, actually it's close to Moscow, it's Khimki, has built the telescope. And you all know these guys, even if you have never heard the name, but you should have, because these are the guys who have built all the Soviet missions to the Moon, to Venus and Mars. And they have also built absolutely wonderfully our telescope. And now imagine how technically challenging was this task, because the shortest observing wavelength at which we operated was 1 centimeter. And the accuracy of the surface had to be at least 10 times better than 1 centimeter. So it means that the accuracy of this surface should be 1 millimeter. So imagine that you launch it on a rocket and it shakes very hard, and very hard during the launch, and all the different issues which potentially might arise from launching such fine instruments to the space. Then you unfurl it, and you make it 10 meters in diameter, and on this 10 meters diameter size, you should have the accuracy of the surface not better, not worse than 1 millimeter. They have successfully done that, and starting from 2011, we are operational. We were operational, and so this slide already summarizes our basic facts about us. And let me just go through a few, which might be the most interesting and which I didn't discuss already. So we were observing at the wavelength between 1 meter and 1 centimeter, and a very challenging task, again technically extremely challenging, was to deliver the data to the ground. And we have used special ground instruments for that. So we were unable to record the data on board the satellite and on a buffer, and then download it from the space to the ground at a later point, because the data flow was so large that we had to send it to the ground real time. So real time, we had to have an observation and sending the data to the ground. So imagine that we had this 10-meter telescope pointed to a space object which we were observing, and then this tiny, but it is 1.5 meter in diameter telescope, which was pointed real time to a special ground telescope, sending the data to this telescope. And we had two of them. Here are the pictures. One of them is close to Moscow, in its Moscow region, in Pushchino. It's on the right-hand side, 22-meter telescope. And then another one, it was covering the eastern hemisphere, and then this one, which was more than 40 meters in diameter, and the American telescope, again, which was located in West Virginia, covering the western hemisphere. So these telescopes were special telescopes which were getting the data from our satellite, and also helping us to determine orbit or orbit parameters of our satellite with very high accuracy. Another one more extremely challenging task was to synchronize the space data, the data which we're getting on our space telescope, to the ground, to ground telescopes which were observing with us. And this was done using a special atomic clock, hydrogen maser atomic clock, which was built by our company, Russian company, Время Че, which is located in Nizhny Novgorod. And it was their first active atomic clock, active hydrogen maser, which was space qualified and which went to space. And it was operational for a long time. It operated extremely well, and it has delivered up to the specs the required level of accuracy of synchronization of our data. And we truly thank the guys for that. Why don't I actually show to you the picture of this maser? So on the right hand side here, you see the maser, which is being tested in our laboratory before the launch. And on the left hand side, there is an example of what are we trying to achieve while using this maser. All right. So we need to synchronize our data between radio telescopes within an interferometer in order to be able to integrate for as long as possible, improving our sensitivity. So on this plot, on the horizontal axis, you see the integration time, the time during which we integrate the data, and on vertical axis, you see the signal-to-noise ratio. And if we integrate coherently, so within integration, we do not lose part of the signal, then this dependence should look like square root of time. And this is logarithmic scale, and the blue line is actually square root of time. And the red points are results of our measurements. And you see that red points sit on this blue line, on square root of time curve or line, almost up to 3 minutes, even, okay, about 3 minutes. Is it long or is it short? It is actually wonderful, because it is 1 centimeter observation, and at 1 centimeter, unfortunately, the radio waves which go through the atmosphere of the Earth, they are affected by this turbulent atmosphere, and because of that, the data are degraded. Not the data which we record on the space telescope, but the data which we get on the ground telescopes, the ground part of our ground to space interferometer. However, if we use just ground telescopes, this coherence will be even shorter, so we wouldn't be able to integrate for longer than about 100 seconds or 2 minutes. So the space does allow us to integrate longer, and it is also the best proof that our hydrogen maser, our atomic clock, works very well. And if I'm not mistaken, and I'm not mistaken, this is the first active atomic clock which has survived in space for a very long time, for several years. Okay, we have used several special computers. We call them software correlators in order to correlate our data. So to correlate the signals between the ground telescope and the space telescope, ground telescopes and the space telescope. And they were located in Russia, in Germany, and in Netherlands. About 60 large and largest radio telescopes on the ground have performed observations with us, and I just showed to you here some examples of them. And these are telescopes from Russia, from Ukraine, from Europe, Western Europe, from United States, South Africa, South Korea, China, Japan, Australia. I think that now I have not forget anyone. So if you have ever seen a large radio telescope, most probably it has observed with us. Okay, what have I? Yes, and another important point is that since 2013, so we have launched in 2011, we had the first phase when we were testing everything, then early science phase, and then since 2013, our mission became 100% open access. This means that any scientist or any group of scientists around the world were able to reply to our call for proposals, suggesting different science ideas. We had an international program evaluation committee, and every year we would form our observing program on the basis of the best proposals which would be selected by this program committee. And this was happening starting from 2013 till the time when we finished our operations. In early 2019, in January 2019, we have lost communication to our satellite, and this was the end of our operations. So we were up and running for about 7 years. It was much longer, I should say, than we expected, because the warranty period was 3 years for our mission. The lifetime expectation was not more than 5 years, and we survived for 7. So this was truly great, and we managed to realized all the key, so to solve or to observe all the key projects which we have selected with our satellite. And we have collected so much data that while a lot is already published, I think that at least 1/2 of the data, if not more, is still being analyzed and will be published within the next years. Okay, let me move right now to science. And okay, why don't I first show this? I don't like this slide with too much text, but just to have something to show to you. We have observed on the sky many different types of objects. These were extragalactic nuclei, so distant quasars, active galaxies, masers, so clouds of water vapor which produce maser emission, pulsars, so neutron stars, dead stars, which rotate and emit extremely bright light. Moreover, we even have performed a so-called gravitational redshift experiment when we were comparing the rate of atomic clock on board the satellite with the rate of atomic clock on the ground, and we have a prediction of general relativity of how they should differ. And by performing this kind of analysis, we were able to test the general relativity theory. an important and kind of unusual feature of the whole mission was the fact that actually, before launching the satellite, we were not guaranteed what will come out from it. We didn't know what will happen because no one ever has observed the space object with such high angular resolution. And could easily have happened that, for example, the bright cores of quasars are not that bright and they wouldn't be even detected by us. They would all be resolved by us with this extremely high angular resolution. It could have happened, and I must admit that we have expected that pulsars will be scattered, because pulsars are strong emitters at long radio wavelengths, and long radio wavelengths are scattered while they propagate through interstellar medium. And because of that, again, they will appear much larger than they actually are, and Radioastron could have resolved them and we wouldn't see them. It turns out that all the types of objects which we have observed, active galactic nuclei, pulsars, masers, they were all detected up to extreme resolutions provided by our ground-to-space interferometer. Again, very surprisingly to us. And let me right now go into that in details. Okay, so I will start with quasars because of two reasons. Reason number one, because I like them. This is my science. This is what I do. And reason number two, actually, that is true most of the time spent observing by Radioastron was observing active galactic nuclei or quasars. It is not because I have chosen that, no. I was coordinating the science program of the mission, that is correct, but I was not part of the program evaluation committee, so we were doing what they would tell us to do. Okay, starting from quasars, let me just spend a few words for people who participate in this webinar but don't know what quasars are or active galactic nuclei are, if there are such people, just some seconds on that. So we believe that in the very centers of such objects, which are located very far away from Earth, on a distance of billions of light years, we believe that in their centers, we have supermassive black holes with a mass on a level of 1 billion solar masses or more. This supermassive black hole in the middle is getting matter, which is accreted, falls down to the black hole from this accretion disk. The disk which consists of gas, of dust, and this matter which falls onto the black hole feeds this black hole. But in addition to that, about 1/10 of this matter is accelerated and ejected out from this central part of active galaxy, ejected out in a form of very narrow collimated relativistic bright jets. Relativistic means that plasma in this jet is moving with a speed which is close to the speed of light. Okay. The first project which I'm going to discuss with you, and as I explained in introduction, I will explain things starting from quite simple level, and then we'll go deeper. So the first project which we have observed with Radioastron is a so-called survey of active galactic nuclei. The main goal was to measure brightness of the cores of distant galaxies, of distant quasars. Why is it interesting? For many dozen of years, scientists believe that they understand the physics of emission of quasars. They believe that, all right, we have electrons which are accelerated somehow, and we believe that we know how. I will talk about this later. They are accelerated to speeds which are close to the speed of light in the middle of this object. All right, they are ejected along the jet, and here is an image of one of the jets. Okay, and they emit a so-called synchrotron radiation. However, there was a prediction that if this is indeed the case, cores of quasars, these bright spots in the beginning, so close to the central supermassive black hole, we believe that, so if it is the case, synchrotron radiation of relativistic electrons, then these cores of quasars cannot appear brighter than certain limit. And this limit is determined by a so-called inverse Compton scattering. So the reason why these cores of quasars, why these plasma regions will cool down and very dramatically and quickly cool down below this predicted theoretically limit is the following. These relativistic electrons, if they emit very bright radiation, they apparently produce a lot of radio photons. And these radio photons will be everywhere around electrons, and electrons will collide with photons and will pass to the photons their energy. So the photons will jump from radio band to optical, from optical to, I don't know, ultraviolet, then to X-rays and gamma rays. And electrons in turn will very quickly cool down, lose their energy. All right, so this predicted theoretical limit was checked observationally, very actively for a long time, and was confirmed using ground interferometers. Unfortunately, the size of the Earth is not large enough to actually allow scientists to be able to be sensitive enough, I mean, to be able to measure this high level of radio brightness in order to truly test this prediction. We had to go to the space, and that is what we have done. And here there are results. So on top, this is the histogram of the brightness. So we measure it in so-called brightness temperature. Let me not go into details. And some value which reflects the level of brightness of cores of quasars. So here it is, a histogram what we knew before. And this is the histogram of what we got from Radioastron observations, right? And you see that on the horizontal axis, which is logarithmic scales, it is the same interval. And you see that the Radioastron values have moved the histogram to the right by almost at least 1 order of magnitude. So we have observed more than 100 of these quasars. We have detected many of them. If you are doing extragalactic astronomy, then you see here your very well-known pets on the screen. So the blazars O235 or J287, 3C279, etc., which turn out to be extremely bright and extremely compact. But altogether, important is that the whole sample, large sample of quasars, turns out to show level of brightness at least 10 times higher than what was predicted and what was actually observed before. How can we explain it? So this is quite deep physics. Let me go through this. So how is this possible? So option number one is that there is an effect which is called a relativistic aberration. If you have not heard about it before, you can even read about it in Wikipedia. In a few words, this effect results in plasma appearing brighter than it actually is if a plasma blob, a plasma region, is moving in the direction of an observer with a speed which is close to the speed of light. But there are ways how we can estimate this boosting, this relativistic boosting. And by very carefully checking the level of this boosting, again, there is about 1 order of magnitude not enough to explain what we see. The second point could be so-called continuously excited core. So there might be some mechanism which excites relativistic electrons far away from the central nucleus, even if they lose their energy through the inverse Compton scattering, which I have discussed before. But we should not forget that these cores which we observe, they are located parsecs away from the central nucleus, so that actually it is very difficult to imagine such mechanism. In principle, magnetic reconnection might play some role there, although it doesn't look very probable. I will be happy to go into details if there are questions. And the third point, which looked very improbable to us at the beginning, and which turns out to be more and more interesting, is the possibility that what is actually happening is relativistic, is synchrotron radiation of relativistic protons instead of relativistic electrons. The reason why originally we didn't consider this seriously is because theorists actually don't know how to accelerate particles to, how to accelerate protons to relativistic level in nuclei of active galaxies. Protons are 2,000 times heavier than electrons. So it's 2,000 times more complicated, right, to accelerate them. It is truly very difficult. So it didn't look serious to us. However, very recently there is a number of papers, including our paper, which was recently accepted by ABJ, which relates radio bright quasars with extremely high energy neutrinos detected by the IceCube telescope, which is located at the South Pole. And in order to produce high energy neutrinos, you need to have relativistic protons. So you can produce neutrinos either by proton plus photon or proton plus proton mechanism. And it turns out that the same objects which are found by Radioastron to be extremely bright are associated with high energy neutrinos. So this very recent result, it was accepted by APJ, like our paper, like a week or two ago, supports this last bullet on this slide, suggesting that relativistic electrons might be the source of extremely bright radio emission, which we see from distant quasars. Okay, let me go on. Another interesting example of scientific results which we have achieved with Radioastron is measuring polarization and using polarization information in order to reconstruct magnetic field structure in distant galaxies. And magnetic field plays crucial role in the process of jet acceleration. So the structure of this magnetic field is extremely important. It's extremely important for us to know, right, to understand what is the structure of magnetic field. And here on the left-hand side, you see by white ticks the direction of electric vector position angle, so direction of linear polarization. And by color, you see the Faraday rotation. And you can see the gradient of Faraday rotation in a core of an active galaxy, which is called BLAC. And we were able to reconstruct this Faraday rotation gradient and this gradient or this change in direction of linear polarization direction by a numerical 3D relativistic magnetohydrodynamic simulations. And we were able to do that assuming that the magnetic field is toroidal. So this is very important because this actually means that our understanding on the role which magnetic field plays in jet acceleration is correct. So there is a toroidal field which helps to accelerate particles very close to the central supermassive black hole, which is located somewhere here. Apparently we don't see the black hole. Another example is observing the so-called BLAC object a blazer with the name OJ287. Again, we observed it 1 centimeter, and changing the angular resolution from left to right, it is improving. It becomes better and better, and here it comes to this extreme values of 10 microarc seconds. We can see that the shape of the jet, of this ejection of relativistic plasma in this blazer is curved. So basically we observe a precessing jet thanks to Radioastron, thanks to its very high resolution. And precessing jet is exactly what was predicted for this quasar, predicted but not observed before. I mean, we were just not able to. Predicted for this blazer because there was a suggestion made that this is a good candidate of a blazer having a binary black hole system in their center. And if you have a binary black hole, there is a high chance that by rotating binary, your jet will become precessing. That is exactly what we see here. So we confirm the binary black hole suggestion idea for this blazer. Okay, another very interesting example is nearby galaxy by the name 3C84. And okay, let us look first on the right hand side. Since it is located close to us, our angular resolution results in extremely high linear resolution. So this is only 1000 Schwarzschild radii. So the supermassive black hole is located somewhere here, and this is the jet which is emitted from the center of this galaxy. And you can see that we resolve this jet very well. Surprisingly, the jet turns out to be empty, dark in the middle. We don't see emission, or we see very little emission coming from the center of the jet. Does it mean that the jet is indeed empty in the middle? Most probably not. We believe that what we see here is a so-called stratification of a plasma flow, a situation when the speed of the plasma in the center of this jet, and let us look right now here on the to the left hand side. So the same jet, it is this zoom in the central part, and so here we see the jet, we see the edges of the jet, and so we think that plasma in the center moves with a speed which is higher than the speed of the edges. As a result of that, due to relativistic aberration, all the emission from the center of this jet is beamed away from an observer on the Earth. And all what observer on the Earth can see is emission of the edges of this jet, of the edges which move at a much slower velocity. Why the velocity is much slower? Most probably due to interaction with surrounding the jet interstellar medium. Another extremely interesting result came out from the fact which you can see again on this slide on the left hand side. We were able to measure the width of the jet. I mean, in the past we were unable to resolve it. Angular resolution was not enough, was not high enough. Right now we can resolve it, and it turns out that the width of the jet is several hundred Schwarzschild radii, actually up to 1000 Schwarzschild radii. So the jet starts from the very beginning being extremely wide. And I promised to you to discuss the mechanism how the jet is launched and accelerated. And there are two mechanisms proposed in the name of their authors. So Blandford-Znaik versus Blandford-Payne. Blandford-Znaik mechanism suggests that the rotating momentum of the central supermassive black hole is used to form the jet. And Blandford-Payne mechanism suggests that rotating momentum of the accretion disk is used to form the jet. Okay, it's apparent that the accretion disk is much larger than the central supermassive black hole. So it might be the case that here right now in front of you, you see the first clear example of the Blandford-Payne mechanism forming the jet in a distant galaxy. While in the past, we all believed that Blandford-Znaik is always playing a role, and the central supermassive black hole is responsible for generating the jets. So here is the first example that the accretion disk plays an important or even crucial role in forming relativistic jets in distant galaxies. Okay, let me move on, and just a few more nice examples of the images which we have received. And on the left-hand side and the right-hand side is the same quasar 3C273, actually an object which has helped scientists to discover quasars, to realize that quasars are distant galaxies, very bright distant galaxies with bright nuclei. And this colored spiral, or how to call it properly, these colored images which you see here show to you results of observing this jet with Radioastron at 18 and 6 centimeters. And we see an extreme stratification. You already have heard this word from me, to the extreme stratification of the plasma flow. And because of that, at 18 centimeters, so here in color, we see the edges being extremely bright of this jet. And here at 6 centimeter, we see the central part of the jet being extremely bright. Talking about studying the plasma flow in jets, I can show you one more example. It is the very well-known M87 with its wonderful jet, and you can already see here, already on this image, see a very nice spiral in this jet, yes, all along this jet. And I can zoom in and you can see the spiral even better. And this is a wonderful example of Kelvin-Helmholtz plasma instability growing in jets, which is zoomed in for us in this jet by Radioastron. Another example, so in orange, you might see how we were able to reconstruct images of distant quasars in the past. Basically, you cannot see anything. So orange is what the ground interferometers brings you. And in blue, you see what Radioastron gave. Again, a very good example of Kelvin-Helmholtz plasma instabilities growing in jets. And there is a paper published recently by our PhD student, Max Planck, Vega Garcia. You're welcome to read in details what we have found out there. So again, in orange is the beam, so the resolution of the ground interferometer, and in blue is the resolution of the space. So imagine that this is basically 1 pixel of the ground interferometer, and this is 1 pixel of Radioastron. Okay, I'm moving right now to masers. And in Radioastron, we have observed both galactic and extragalactic masers. On this slide, I show one example of an extragalactic maser. So it is a galaxy with accretion disk, and we can resolve this accretion disk, and we can study water vapor clouds in accretion disk of this galaxy. And actually, this particular object has delivered to us the detection of a signal at the baseline of 26 Earth diameters from Radioastron, and most probably we still do not resolve it. So the clouds should be of the size of less than 3 microarcseconds. There, it could be that we observe even star forming regions, and it is found that the thickness of accretion disk is actually very small, about 10 microarcseconds, and it helped us to constrain kinematics and dynamics of the disk. An example of galactic maser, Cepheus A, extremely compact source, again of a water maser emission. The size again is estimated to be comparable to the size of our sun, and results might be understood as possible turbulent von Karman vortex street. Again, it could be read in APJ by Sobolev et al., published in 2018. Let me, I see that I try to stay within 1 hour, so I have about whatever, 7 or 8 more minutes. And let me right now move to pulsars. Pulsars have delivered the most unexpected results to us. As I have said in the beginning, shortly, pulsars are extremely interesting, right? So these are dead stars of the size of 10 kilometers, right, in diameter. They rotate very quickly, and magnetic field is extremely high, and we can see radiation from their magnetic poles. And since they rotate, this radiation looks like pulses on the ground, and we see them like pulses. But since pulsars are strong at long radio wavelengths, as already said, their emission is scattered. So it is like observing a street light through a fog. They look much larger than they actually are. And radioastron, having this fine, extremely high angular resolution, filters out all the extended emission. So basically, we did not expect to see any signal from pulsars while observing them with increasing radioastron baselines. And let us look right now on the left-hand side. And here on the horizontal axis, this is the projected baseline of our interferometer, so size of our interferometer. The longer the baseline, the higher the resolution. Logarithmic scale, horizontal and vertical as well. And on the vertical axis, you see the level of the signal which we measure. And these data points come from the ground measurements, just between telescopes which are located on the ground. And this comes already from the space, and this is the curve which we expected to see in case if our pulsar is resolved. And this is what we have expected. Surprisingly, this is what we got. So all these data are our measurements of these particular pulsars, which I use as an example, with American GBT and Netherlands telescope, Dutch telescope in Westerbork, WSRT. So these are the measurements which you get, which are many orders of magnitude higher than we have expected. For about 1 year, we were thinking how this could be explained and what is going on, and we have checked it on different radioastron baselines and on different pulsars, and it was all confirmed. And it turns out that so we believe that right now we understand what is going on. As a result of this discovery, we have basically found a new scattering effect, which has extended very deeply our understanding of the scattering theory, and also helped us to study properties of not only pulsars, but other objects as well. Let me tell you in a few words. So here is an example of what we think is going on. So here you can see it is a model image. Imagine this is a pulsar, and it looks as large as you can see it on the screen. It is not so large, but it's just scattered. But on top of this scattered emission, you can see tiny dots. And these tiny dots, which you can observe on top of this smooth scattered picture, is exactly what determines these data points, what defines these data points. And we believe that this is a result of an interference of a multiple image, of many images of the pulsar, which are generated in many turbulent cells of an interstellar cloud. So because of this interference, we have these dots, these tiny spots, which cover the scattered image of the pulsar. If this is the case, then the scattering should not depend on a pulsar. And yes, we observe this effect from many pulsars, but we can also predict this effect to be the case while we observe other objects. For example, the center of our galaxy, Sagittarius star. And we have predicted that, performed observations, and here you see the result. Very similar picture. So at the center of our galaxy, with a very interesting, supermassive black hole there of for a million solar masses, and very interesting physics there. Its emission is scattered, and that is how it looks like on an interferometer. But then again, instead of for the dots going down, following this green line, following what is predicted by scattering theory, we detect emission from such a star at long projected spacings of an interferometer, which confirms that the same is the case observing such a star. And this is extremely important because we can use this effect not only to measure properties of an interstellar cloud, which results in the scattering, not only properties of the interstellar medium, but we understand now that this effect should be very carefully and properly taken into consideration, into account, while interpreting results of interferometric observations of objects which are hidden from us by the interstellar medium. And this is extremely important in order to study center of our galaxy, right? Because we have heard about the black hole shadow, which astronomers have observed from M87. But what we very much want to do next is to see the black hole shadow from the center of our galaxy, right? Because only for the center of our galaxy, we know the mass of black hole very well, we know the distance very well, so we can even test the general relativity in this region close to the supermassive black hole with very high gravitational field. But in order to do that, we should be able to reconstruct the image of the center of our galaxy with very high accuracy. And in order to do it properly, this effect should be taken into account. What next? Radioastron is over. The science teams continue analyzing, reducing and analyzing the data, publishing papers. There is still a lot to come. I have covered only like a tiny bit of what I have chosen to be hopefully interesting for you today. But we are already thinking about the next step. So Russia is right now working, Russian Space Agency with my institute, Lebedev Physical Institute of Russian Academy of Sciences, with many engineers in Russia and around the world. We are working on the next generation space LBI mission, which will be called Millimetron. Apparently, from the name, it is expected to operate at short wavelengths, at millimeter wavelengths, and even sub-millimeter wavelengths. And one of the reasons why we want to do it is we indeed want to see the shadow of a black hole in the center of our galaxy and the centers of other galaxies, study the supermassive black holes, even possibly look for wormholes, because some theorists believe that this might be real objects, and check if they do exist in the universe, and do test general relativity close to central supermassive black holes in our galaxy and in other galaxies. Let me finish with that. Thank you very much, and I will be happy to take your questions. Thank you.
Thank you very much, Mr. Kovalev. And actually, we have one question already. Mr. Loire, do you prefer me to read it, or you would like to ask it yourself? Monsieur Loire, Nicolas Loire, préférez que c'est moi qui lise votre question, ou vous voulez la poser vous-même? Well, I think I will read it. Yes, do you hear me?
Yes, I can hear you fine. Yeah.
Yeah, okay. So I will read the first question that I got, and then actually I would like to remind that everybody can just raise the hand, and I will give you the floor to ask your question. So the first question: Dear Professor Kovalev, I know a radio telescope existing in the center of France at Nancy, in the department of Cher. I visited it 40 years ago. I have noticed that it was missing in the list of ground-based radio telescopes existing all around the surface of the Earth. Could you please explain the reason why it has not been used in the Radioastron experiment? Thank you for your reply.
Yes, thank you very much for the question. There are actually a number of telescopes in the world which are from one end big and sensitive, but for another end they cannot participate in observations of radio interferometers. And I will tell you more. There is a so-called European VLBI network. There is a European network of telescopes which unites many telescopes around Europe, and actually more than Europe. It also includes China and a few other telescopes. NANSE does not participate in observations of European VLBI network as well because of the same reason. It is not a single dish which can point to a desired position on the sky at the moment when we want it and follow this position. This is so-called a meridian type telescope. It can follow objects for some time, but not any object at any moment of the time. So basically you cannot command it to point at your at an object on the sky of your choice. And you have a network. You have a network of many telescopes on the ground and one telescope in space, so that all of them should be able to monitor, right, to point on a given source and observe it for a long time. Unfortunately, NANSE cannot do it. I can give you another example. There is a similar telescope to NANSE in my country, in Russia, which is called Ratan 600. Similar kind of telescope. This telescope has helped Radioastron very much, observing the same objects, but not being part of our global ground to space interferometer for the same reason, was unable to point to a given source at a given time. It doesn't mean that the telescope is good or it is bad. And different telescopes are built to cover different niche, right? To perform different kind of observations. And NANSE was not just being built to become part of this kind of global interferometry. So we do have our colleagues from France participating in this kind of science and this kind of observations, but not with French telescopes, not with French instruments, but with their experience, with their brains. For example, I was talking today about applied usage of very long line interferometry. So using VLBI, these interferometers, in order to measure positions of distant galaxies with high accuracy, measure positions on the sky, on the ground with very high accuracy, supporting the navigation systems, right, global navigation systems. So there is a strong group in Bordeaux which is doing it as part of our effort, and actually being part of European interferometric effort because of that. Over.
Thank you very much, Mr. Kovalev. The next question from Mr. Alain Baudry. Je vous donne la parole. Oui, Monsieur Baudry, on vous écoute.
Yes, I am here, yeah. Okay, I'm Alain Baudry, yes. The answer about NANSE telescope was very good. There was also another comment you could have done, Yuri. It's about the highest frequency. NANSE cannot go up to 22 gigahertz.
You're absolutely right about the highest frequency. However, you know, it is sort of this. Some of the colleagues might have this kind of snobby comment about the highest frequency, right? Because the highest frequency delivers to us the highest angular resolution. And yes, most of the people who were working with Radioastron, yeah, they were expecting most of the science coming from the highest frequency. This is correct. But as I said, very surprisingly, it turns out that lower frequencies, which are actually okay for NANSE, right? 18 centimeters, and our longest frequency, 1 meter, delivered this absolutely unexpected discovery for us of the scattering substructure, of this strange scattering behavior of interstellar medium. And there, the main role in these observations from the ground was played not by this, you know, high frequency telescopes like, okay, you know the names, right? But was played by Westerbork and by Arecibo, right?
Yeah.
Both of them not being able to go shorter than, let's say, 6 centimeters. So surprisingly, we were able to use all or almost all big telescopes around the world, either at long wavelengths or at short wavelengths, to deliver something exciting. Yes, but some telescopes cannot point like your Nancy or our Ratan, but it doesn't mean that they are bad. They're just doing wonderfully their things.
Yeah, in fact, my question was different.
Yes,
it
please
is
go ahead.
about the maximum angular resolution which has been achieved for cosmic masers. And this is, I think, something around 10 microarc second for extragalactic H2O masers.
You're right.
And a little bit more for the galactic H2O masers. My question is simple. Is there any good scientific reason to go beyond that, supposing that in the future you could have an even bigger baseline length? Do you think, I think I mentioned in my mail that the answer is not perhaps trivial, but it would be nice to know whether this is of interest or not in the future.
Thank you for your question. Could you please clarify, are you asking specifically about masers or about improving the resolution in general?
Well, improving the resolution in general means to go to higher frequency, but I was thinking in water vapor masers at 22 gigahertz, essentially. So I wonder whether there is good scientific cases to improve that or not.
Thank you. Thank you for your question. So just in a few words, because I will use your question in order to discuss improving the resolution in general. Yes, the obvious science case which is being discussed right now around the world, in Russia, in Europe, and in United States, and elsewhere, is the science case apparently pointed towards black holes, right?
Mm-hmm.
And talking about the black hole in the center of our galaxy, we are not so much interested in improving the resolution from what we have already with the Event Horizon Telescope, because it is enough. What we are interested in, right, is improving on the signal-to-noise ratio, on dynamic range, and also on our ability to make the images much faster. Because the reason why we are unable, why EHT was unable to generate the image up front. I mean, they're working on it right now, but it's very difficult, right? It's because the Sagittarius star is relatively small and it is changing within, let's say, 15 to 30 minutes. So we have to improve mostly not on the resolution as it is, but on UV coverage, right? On dynamic range, on the image fidelity. However, if we want to probe the general relativity and get properties of supermassive black holes of other galaxies, I mean, not our, yes, of other active galaxies, of other distant quasars, we need much higher angular resolution. And there was a wonderful paper published by my dear friend and colleague Michael Johnson from Harvard and collaborators in Science Advances just several weeks ago. There was a preprint on that, press release on that recently, which has shown that if you go to L2, and the millimetron plans to go to L2, right? So Lagrange point 2, about a million kilometers away from the ground. If you improve the resolution much higher, you will be able, even not reconstructing the images, but just measuring the visibilities, right? Measuring the signals of the interferometer at these extreme resolutions, you will be able to reconstruct properties of the systems, and you will be able to test general relativity. Wonderful idea, wonderful paper, and actually providing additional reasons to work on millimetron and similar missions. Now to the question which you have actually asked about masers. I should
Well,
admit
no, that was a good answer already. I support your view in view of the recent EHT results. Yes, thank you.
Yes, yes, thank you. Yes, so basically what I'm talking to you about EHT is a result of our discussion which we had at Spacefield BI workshop, which was organized in Charlottesville, right, by us just in January this year, because before all this virus craziness started. Okay, so now to measures. Okay, we have asked our science teams some years ago, okay, guys, tell us, what do you think? Would you be able to get more of, truly qualitatively more new science out of improving the resolution of the ground to space interferometer by, let's say, a coefficient of a few, if we were just thinking if we could push our space telescope to much higher orbit. We were discussing it with not only with science teams but also with Lavashkin. Actually, at the end, Lavashkin told to us, no, you cannot do it because of technical reasons. But before Lavashkin said no, we were talking to science teams, and all the science teams told to us that, guys, if you improve it just by a coefficient of a few, we don't think that we will get a lot of new science out of it. I understand that what our science team working on mega masers, on extragalactic masers, wants to do is to apparently be able to see better these extremely compact regions in the thin accretion disks, to actually be able to answer the question, is it a star forming region which they see, is it something else? They truly want to be able to measure the sizes of these water vapor clouds in order to understand them better. So is it a strong enough reason to, let's say, build another mission and to launch it far away for that, and then to observe it at 1.3 centimeter? Possibly not. However, if we will have a 1.3 centimeter receiver at millimetron, this is still being discussed. The problem is that 1.3 centimeter is quite large just in size, and to fit it there, it is a question, and some people are fighting for it, some people are fighting against it. So we'll see if you have it at millimetron, and then if you will be able to continue this water vapor maser science on millimetron. I hope I managed to answer your question.
Yes, that was very interesting. I don't believe either that the water vapor masers would deserve better spatial resolution in NGC 4258. I don't believe, for instance, that the individual components are star forming regions because this region is quite hostile to surviving, and so that's one reason. But there are other reasons, I think. So I understand the choice for millimetron. Yes, 1.3 centimeter is perhaps not fully deserved.
Okay, thank you very much for your comment.
Thank you very much, and I think we can pass to the other question. Thank you very much, Monsieur Boutry. Well, the next question from Ayman Marwani. Why this space telescope didn't participate on the Event Horizon project?
Okay, wonderful question. Thank you. Why don't I have this wonderful picture right now on the screen? You know that the space is always behind the ground, technologically. You can launch things to the space only after you have tested everything and everything works fine on the ground. And it takes years after you have developed all the new technologies on the ground in order to manage to send it to the space. So it all goes in it's one should happen after another. And right now we have shown that Spacefield BI works at centimeter wavelengths, and not only works, but actually works delivering extremely high, actually record-breaking angular resolution. So to become part of Event Horizon Telescope, or better to say, to be the next step in this activity, you need to develop new systems, and that is exactly what we are doing right now with millimetron. And that is exactly what we are right now discussing together with international community. And while talking about millimetron, I would like to sort of follow up on what I have already said about goals of millimeter and sub-millimeter space field BI for the future. We need to be able to produce images of such a star within, let's say, half an hour, 20 minutes. We can use, and it is being discussed, to use satellites for it, which are low orbiters, which orbit around the Earth very quickly, so the period of their orbit is very short. It will actually require extremely strong support from the ground, because we will have to have a number of tracking stations all over the Earth to get the data out from these telescopes. And by orbiting very quickly around the Earth, it will allow us to cover the UV plane, right? If you are VLBI, you understand what I'm talking about, and then reconstruct the image just within some minutes. Because of the fact that the Earth rotates within like 24 hours, and we generate a virtual telescope due to Earth rotation, let's say within 8 hours, 10 hours, doesn't allow us to properly image event horizon scales of such a star, because it changes much faster than the time during which we accumulate the data and then reconstruct the data. So this is talking about the satellites which will be low orbiters, and most probably we are talking about more than one of them. But in addition to that, as I already said, you might want to send very sensitive dishes far away from the Earth, to like 1 million kilometers away, to study not only the center of our galaxy, but centers of other distant galaxies, and to form so-called black hole zoo, studying black holes on cosmological scales. Finalizing this answer, by finishing this answer, let me also tell one thing. Apparently, we tried to observe the center of M87 with Radioastron. It would be stupid not to try. For such a star, we knew, okay, so this is M87, and here is its center, all right? And we knew that such a star is out of any question because of the scattering at 1 centimeter. The scattering is so strong, you cannot see anything. There is a dense cloud in between the Earth and the center of our galaxy. But talking about M87, okay, was a nice try. So we observed it at our shortest wavelength. Our shortest wavelength, not only because it provides the highest angular resolution, but also the shortest wavelength is the best against scattering and against synchrotron self-absorption in the center of M87. And we knew that, okay, I mean, we could be lucky, we might not be lucky. We observed it. We had several most sensitive experiments one can organize using the most sensitive, the largest dishes on the ground. And yes, unfortunately, we couldn't see the center of M87, although we had resolution comparable to what EHT has, even better. But unfortunately, the center of M87 is scattered. And moreover, it's not only the scattering, but it is absorption. So the emission which is coming out from the very center of M87 is absorbed at our shortest wavelength, 1.3 centimeters, so we couldn't see it. Over.
Thank you very much. So the next question from Mr. Kevin Ritzenthaler. I'm not specialist, but are there projects to launch 2 telescopes in the same orbit and increase accuracy of observation thanks to larger increased baseline? Or is it too challenging, difficult to synchronize clock with 2 telescopes in orbits?
It's challenging, but the problem is not that. It is expensive. So let me give you the full story, but I will try to be short. The first idea of sending more than 1 telescope was suggested by our Chinese colleagues, by Chinese radio astronomers and Chinese Space Agency. The problem was that our colleagues didn't suggest to go to very high frequencies. They basically said, all right, we will observe at centimeter wavelengths, possibly at a little bit shorter than 1 centimeter, but we will not go much shorter because it is technically too challenging and too expensive. And we will launch 2 telescopes, and because of that, our images will be superb, and that is true, actually. They would be very nice. Unfortunately, this kind of project, at that time, it has happened several years ago, did not promise any breakthrough science. So because of that, it was not chosen by Chinese Space Agency to be funded at that time. Our Chinese colleagues continue working on that, but not very actively. Right now, because of the success of Event Horizon Telescope with M87, it is being discussed to launch more than 1 telescope within with the goal to see the black hole shadow from such a star and from M87 and a few other galaxies, probably more than that. Actually, you know, it is not challenging to synchronize them because you will synchronize them separately, one way or another. You can synchronize them by putting your atomic clock at every satellite. It is quite expensive and heavy. You can also synchronize them by using the ground atomic clock and syncing them to the ground through some special systems, which I did not discuss today, but Radioastron has such system as well. So this will work. It will just be more expensive. More telescopes in space means that, okay, you should have heavy launchers, you should have lighter telescopes, you should have more systems on the ground, working with them, you know, getting the data, etc. There is also, so our American colleagues actually talking from EHT group from Harvard, are thinking about several light telescopes. Several is probably too strong of a word, like 2 or more, to be launched like low flyers. Our European colleagues from Netherlands are talking about 2 telescopes which will sync to each other through laser link and which will do everything by themselves. So they will actually not even need ground telescopes. It will be only space-to-space radio interferometer. There are pros and cons of both ideas, both suggestions. All of them are very expensive. All of them will not happen tomorrow. They will happen in many years, if at all, because right now ideas are being worked on and suggested to space agencies. We'll see what will happen. Over.
Well, thank you. The next question, maybe it's similar to the previous one, but still, from Mr. Nicolas Gros. Dear Professor, based on my understanding of your presentation, it would seem interesting to use 2 on-orbit telescopes rather than having 1 on ground to avoid the noise induced by the atmosphere. Are there reasons to make it unrealistic?
This is a very good question. Thank you. It is not the same question, actually. It is the question which I didn't cover, is why 2 space telescopes is not the same as 1 on the ground and 1 in space. If you can improve, you know, on the atmosphere, etc. So the problem is, colleagues, that basically the largest what we can launch to the space is 10 meters in diameter. Even 10 meters is extremely difficult. Okay, let's think about Herschel, which was whatever, like 2 meters in diameter, and let's imagine how expensive is James Webb right now, being about 10 meters, right? It is extremely challenging. So even 10 meters is extremely challenging. And on the ground, we easily have 100 meters. Okay, it's not easily, right? All right, in Chile, we have ALMA, which is a collection of more than 50 telescopes, and altogether it is like of an order of 100 meter dish at millimeter and sub-millimeter wavelengths. An interferometer, a sensitivity of an interferometer is square root of a sensitivity of 1 telescope times sensitivity of another telescope. So having a large ground dish compensates for having a small space dish in sensitivities. So by working, by only having two telescopes in space, we have a very low sensitive instrument, a very low sensitive interferometer space to space. You could argue that, all right, but you have said yourself that atmosphere is a problem. And since there is no problem with the atmosphere in space, we can integrate basically forever or as long as we want. No, we cannot integrate forever because the signal does change. And from the changes of the signal through the time, we do actually reconstruct the images. So we cannot average and integrate forever. And there are many other restrictions, coherence time due to synchronization of atomic clock. Apparently, atomic clock are quite sensitive. It's okay. The current ones is easily stability is 10 to the power of minus 14 seconds per second, and probably you can build something like to the power of minus 15 or even 16. But again, space to space, you will be limited. Your coherence time, your integration time will be limited not by the atmosphere, but by stability of your atomic clock. Over.
Thank you. So the next question from Mr. Baptiste Laurent. So first, thank you for presentation. My question is about telescope location. Indeed, currently there is telescope all around the Earth and in orbit around it. However, this location is not optimal because of atmosphere disturbances. Therefore, can we think to locate telescope on the moon in the future or in order to counterbalance those perturbations? For you, does it a potential evolution for space observation? And if not, what will be the future of the space observation telescope?
Thank you very much. I should say that we do discuss putting telescopes on the moon. And there is an active debate on what is actually the best, to have a so-called free flyer or to put telescopes on the moon. And indeed, telescopes on the moon are being seriously discussed. Right now, it seems like the best niche for a telescope on the moon is for a very long wavelength telescope, not an interferometer. I mean, not the moon to the Earth interferometer. And the reason for that is that if you can put a very long wavelength telescope on the moon in a crater on the poles of the moon or on this other side of the moon, we can protect this instrument from a very strong radiation of the Earth at these frequencies. And we cannot perform an extremely long wavelength radioastronomical observations from the ground because of the ionosphere. Our ionosphere does not allow electromagnetic waves of a very low frequency to go through it. So only, this is actually, the extremely long wavelength astronomy is the only part of the electromagnetic spectrum which is still hidden from us. And this last window on the electromagnetic spectrum, it seems will be best covered by extremely long wavelength radio telescope on the moon. And on top of that, it is actually quite cheap because this telescope will be, okay, to simplify, will be just a collection of wires, just a collection of wires covering a crater or something like that will be this telescope. So it will be quite cheap to deliver it there and to perform observations of the sky at this last window of electromagnetic spectrum. Moreover, there is a very interesting task, cosmological task, to study the epoch of reionization at these very long wavelengths and very, very low frequencies, which means looking at our universe from very far away. Talking about an interferometer, it seems that being able to send satellites to rotate around the Earth and have very short orbit to be able to reconstruct the images very quickly, within half an hour. and sending satellites very far away to L2 point, like a couple of million kilometers, is the most exciting opportunity regarding the next step of very high frequency ground to space interferometry. I'm talking about frequencies above 100 gigahertz. Over.
So I don't have any more question in the chat. Does anybody have other questions? Please, dear participants, don't hesitate to ask questions. So I think that
Can I hear the comment,
yes,
please?
we have some more.
Can I hear the comment?
Wait.
Go ahead.
Yes. I'm coming back to the satellite interferometry. In fact, what is important is the dynamic range when you build up your image. And in order to achieve that, it's much better to have one single dish upstairs and having different telescopes on the Earth so that you have a very large number of projected baselines on the source. And this is an important issue, of course.
Totally agree. Thank you.
Any more?
This is a science lecture. I mean, to ask questions for more than half an hour is quite atypical. So I believe this is the right time to stop, guys. It's not public talk. Yes, there it could go for more than an hour.
So, well, I would like to thank our speaker, Mr. Kovalev. Thank you very much for joining us. Thank you very much for all participants who joined us today. Mr. Kovalev, would you like to tell something else?
Yes, I would like to thank the participants for joining us, and yes, thank you the organizers, etc. But guys, it was a huge pleasure to give a lecture to you, and I would like to thank you for your wonderful French accent in English, because it has given to me exactly what I miss right now. I miss Paris, and through you guys, I got a little piece of France in my soul, which will help to survive through these very difficult times. Thank you very much.
Mr. Kovalev, one more thing from me. First of all, let me thank you for this wonderful lecture and express the hope that we see you again in future, not only in line mode, but also in person at our center in Paris. Of course, after removal of quarantine measures. I would like to thank also all viewers, all participants for your attention. Let me also thank Marina, who was very good. And before finishing, I'd like to remind you that for those who are interested in space and psychology, tomorrow we'll conduct another lecture, online conference, Isolation from the Point of View of Space Psychology, will be given by Russian psychologist Anna Yusupova, a leading researcher of Laboratory for Social and Cognitive Psychology at the Institute of Biomedical Problems of the Russian Academy of Sciences. Please keep in mind the lecture will be in French. So see you again tomorrow at 4 p.m. Paris time. Thank you so much. Bye.
Thank you, Konstantin. I would like just to say to Mr. Kovalev that today it's not only Paris who joined us, but also Bordeaux and some other French cities, and maybe even not only French cities. So
Thank you, Marina.
Hello from Bordeaux, Yuri.
Hello.
Yeah, exactly, Mr. Boudic from Bordeaux, but I think not the only one. And we are glad that we managed to do this lecture in spite of the all conditions, because we wanted so much to organize the in-person lecture of Mr. Kovalev and some others scientists, some Russian scientists in CNES and on other sites in France, but unfortunately we couldn't. So we started with that, but we will continue. Well, thank you very much.
Thank you.
Thank you, guys. Bye and have a good evening.